folks, let's get started. So as you see, I have the results of the survey. I want to point some things out. Well, first of all, you know, after today, we only have 2 more lectures. Does that seem reasonable? That's the end of the semester is just, I mean, it's right there around the corner. So, as I was saying, I think this represents some sort of frustration on our part about Zoom and the internet and bandwidth and whatnot. And this is pretty much what I expected down here. 2/3 just want traditional face-to-face instruction. Another quarter would like to have both. I don't know whether having all of the material available online through Canvas satisfies the criteria of hybrid. 7 people said that. So that's the result. Who said that they had a conflict in their final exam with Physics 216? Ms. Soto. Did you get that worked out?
The professor said that he's using ProctorU, and we're supposed to sign up a time to take the exam. So everyone will be taking the exam at a different time.
Man, I didn't understand any of that. It's really, really garbled.
Yeah, I can send you an email if you would like me to.
Well, I discovered something. The time that I had listed is wrong. This is the final exam schedule. I printed it out just 20 minutes ago. And Monday, Wednesday classes that meet from noon to 1:15. The final is on Wednesday. I think I had it listed on Monday. But the final exam is on Wednesday at 10:30 in the morning. Does that help you?
Yes.
Well, what you have learned is never trust me when it comes to time. As my wife says, I don't do time. If you're a Cheech and Chong fan, I don't do time, man. Okay.
Well, thank you for looking at it.
Oh, yes. Well, I'm glad you brought it up because it, you know, I had to reschedule the Zoom meeting for the right time and stuff like that. I changed it in Canvas, and so, but I think the registrar's office is changing or has changed the final exam schedule since it was first published. But I can't prove that. And I don't know the registrar anymore, so. Well, theoretically, you all have watched the video on the graphics processor. Is this true? I can hear you shaking your heads out there.
I watched it. It was nice.
Was the quality okay?
Yeah, it was good.
Okay. I don't have a lot of control over the quality because I produced that in 1080p and then YouTube converts it to their standard video format. And I don't know what that is. So I don't think it makes any difference how high a quality it is when I produce it. They're going to knock it down to whatever quality they think is appropriate. So it took me forever to do that. I used a new piece of software I have called Multicam, which I thought was going to allow me to effortlessly switch between pumping out the video on one of my screens or one of my cameras or whatever, but I was wrong. What it does is it produces a separate video file for each of those camera sources. And then I have to go in with a video editor and splice them together into what you see. And my video editor, I upgraded to version 23 just, I don't know, a couple of weeks ago. And I had to learn how to use it all over again. So it took me forever, but now I feel more comfortable. So I'm going to produce a new lecture on, what's it on? Oh, it's on pipelining. And that will be available in the next couple of days. And of course, you'll be expected to watch that, get some popcorn and a Coke and sit down and watch that. And we will discuss it on Monday. So that's it. This is your time. What do you want to ask about the graphics processor? See, Charles?
Point taken.
What? I didn't hear what you
Point
said.
taken, sir. Point taken.
Point taken. Okay. Yeah. You all, you need to, if you're going to do this online business, especially with Zoom, you're going to need to develop the skill that many pilots have. And that is, I believe that the Zoom software turns your mic on and off automatically when it hears noise. What that means, so voice operated transmission, what that means is usually the first couple of syllables are not transmitted. So people that do this all the time have a tendency to start a sentence with so or well or or something like that to get the voice operated control working, and then they start actually saying something that's important. No questions about graphics processor. Is that right? Okay. Luis?
I think it was pretty straightforward, so I didn't have any questions.
Yeah, well, it's a proprietary hardware. It's proprietary design. But as I said, every manufacturer has to go through those same steps of, you know, tessellation and all the illumination, and, you know, all of those steps are independent of the hardware. The the difference from one card to another is how they perform that. And it's an ongoing development process. Well, I have a suggestion. I have a PowerPoint presentation, which I like to give at the very end of the semester. And it usually takes a couple of lecture periods to go through it. It is sort of a reminiscence, if you will, about the history of computing. And I've sort of been, at least on personal computing, I've been there for a lot of the developments, so I've got some connection with that. Most of the students find it entertaining. There's not anything in it that would be on a final exam or anything like that. It's basically entertainment value. So I'm going to put it to you this way. We can stop right now and you can go back to sleep because you don't have any questions for me.
I just have one question regarding clusters.
Yeah.
Can you have more than 4 clusters in a GPU?
Well, it depends on the manufacturer. Sure, there's no reason
Limit.
There's no physical limit other than what they think you're willing to pay for it and how big it'll be. You know, it's got to fit and how much power it needs and all those sort of things. But I don't think there's any physical limit to how many little processors can be in there. I know that my GPU, which is I don't even know what it is, but you can actually put in, I think, 3 of them. And they've got these little ribbon cables that you can use to bridge from one card to the next. And they sort of all form a single virtual graphics card. But I didn't have any need for anything like that. Any of you guys serious gamers? You don't have
See,
I mean,
time,
kinda,
right?
I guess.
Yeah.
probably like half of us.
So you probably know more about at least the external features of graphics cards than I do. I don't, I don't pay much attention to that. So are you all interested in a history of computing?
I am.
Yes.
Hey, I'll tell you what, since, it's completely voluntary. If we start this, I don't care if you all go away. I'll just keep my eye over here on this list of who's signed in. And when the last of you leave, I'll stop talking. How about that?
And I have another question. I think
Yes, sir.
my exam for 230 conflicts with 212 now. So
Wait, say that again.
my final exam for 230 conflicts with 212 now.
Okay, when does your math 230 class meet?
It's E 230, and it's
Okay, when does
Wednesday,
Wednesday, when?
9 to 2.
Wednesday from 9 to 2?
You have a
Yeah.
5-hour final?
Because Dr. Harold gives us extra time. Our final is not actually scheduled from that time. That's Dr. Harold giving us extra.
Well, Wednesday, yeah, it meets for a long time because you have to it only meets once a week. So that would be 150 minutes.
No, the class meets twice a week. He's just giving us extra time than would be allotted usually.
Okay, what is the official meeting time for the class?
It's 10:30 to 11:45.
On what days?
Monday, Wednesday.
Okay, Monday, Wednesday, 10:30 to 11:45. Is that right?
Yes.
Sorry.
Well, according to this schedule, that exam is supposed to be on Monday at 10:30.
Oh, I will let him know then.
I mean, I'm looking at the final exam schedule. Here, I'll even show you. Okay, right here, we have Monday and Wednesday classes, 10:30 to 11:45. Is that you? Is that double E 230? 10:30 to
Yes.
11:45, Monday and Wednesday. That's Monday, the 11th at 10:30 a.m. He probably is working off of the old exam schedule too.
Yeah, maybe.
So,
I will let him know then.
okay. Who's,
All right, thank
who's
you.
teaching Math 230?
It's E 230 and it's Dell Harrell.
Oh, Dale. Yeah,
Yeah.
he's so wacky. Just just tell him. Don't ask him, just tell him. Okay, folks. So I'm going to start, unless there are more questions, I am going to start this PowerPoint I have on the history of computing.
I do have one question. I can't recall from the beginning of the semester if you said this, and I touched it in the syllabus, but do you curve at the very end whenever we take the final?
There's so much background noise, I cannot understand what you're saying. I'm sorry. It
Can
sounds
you hear
like,
me better?
Asking if
there's a television going on in the background.
I think she was asking if you curved the final grade according to.
Yeah, I
Yes.
do. I curve each of the individual grades, and then at the end, I curve the final grade. I'm a big believer in curving grades because I think that washes out any unintentional confusion about questions or language or something that wasn't exactly clear to everybody. That washes out in the final because it affected everybody.
I'm a big fan of a 20-point curve.
Minus 20 points?
No, plus.
Well, I don't know if I've ever given a 20-point curve before, but I look at the data, I look at the grades, and I try to find groups of grades. It's with a group, yeah, this is 30 people. It usually works out fairly well, but there's usually a break in the grades. There's a cluster of people that have really high grades, and you know they're going to get A's. And then there's a cluster of people with grades in the middle, and then cluster of people with grades at the end. And then I go look at the people that sort of are on those boundaries. I look back at how many homeworks were turned in, how many quizzes were missed, stuff like that, to see how serious you were about coming. So there's a lot of stuff that goes into it.
And one more question. Do we have a quiz today?
Yeah, there'll be a quiz today. I guess we should go ahead and do the quiz. Because I told you could all leave, right?
Yeah, I think it unlocks at 12:30.
Yeah, let me go change that right now. I guess you're watching me do this, aren't you?
We're seeing the camera with the paper.
Oh, really? Of
Yeah.
course. That's because I didn't hit that little button right there. Now do you see the quiz?
Yeah.
Okay, unlock it. It is available from, what time is it? I'll say 12:15. Okay, somebody go try it. See if you can do the quiz.
Yeah, it's unlocked.
Okay, y'all go do the quiz. Has it been 5 minutes yet?
Yeah.
Yeah, about.
Okay. So, a brief history of computing. I'm going to have to go back in history a little bit. The first machine that we would recognize as being a computer is this guy right here. This is a loom made for weaving fabric. You can see right here, there's some fabric coming out and it's being rolled up right here. And you know that the way this works, the way that a loom works is you pick up some threads and you pull down some other threads, and then you push a shuttle through between the ones that are above and the ones that are below, and then you change the pattern of threads that are up and down and all that kind of stuff. Well, in 1801, this guy decided that he could automate that process, and so he came up with this method. Each one of these cards has got these holes in them, and the holes allow a pin to fall through, and that pin is attached to some of the strings. Well, one string, one hole for each thread. And so this determines which threads are pulled up and which threads are pulled down. And then you run the shuttlecock through, you push on the lever, that advances this one card, and it changes the pattern, and you just keep going. And so we have a series of instructions that are executed sequentially. That's a computer, sort of. I mean, it's got all of the hallmarks of a computer. This is a memory where the instructions are stored. So most people consider the Jacquard loom as the first programmable machine. Then in 1833, this is 32 years later, Charles Babbage built a mechanical machine. He called it a difference engine, and it was designed to solve navigational problems for the British Navy. See, there's a crank over here. This is all analog, okay? And it's designed to solve essentially differential equations. Now, 4 years later, the same guy, Babbage, built a mechanical analog engine that was designed to solve general problems, but he never finished it. And the reason he never finished it was that the technology of the day was insufficient to make the parts as precisely as necessary. It would have been huge. Somebody not too long ago, with modern technology, rebuilt some of this and showed that it would have worked. So this is in the early 1800s. People are starting to do this kind of thing. In 1880, Herman Hollerith designed a data storage and sorting system using punched cards. He encoded data on these cards, and then the cards were put in this machine. It's not a terribly good picture, but you would put the card down here, and then you would take this little stylus and you would go along and you would put the stylus in every hole that was in the card. And when you did that, it made an electrical connection up here with a different circuit for every possible hole. So you went through and you basically said this hole, this hole, this hole, this hole, and those signals were sent electrically. And there it is right there. That's the machine. And these are counters up here. They were dials with a clock face, basically. And every time this guy went through a hole that was connected to one of these, it would advance one. So one of these might be, how many people, you know, no, that's a bad question. Do you have indoor plumbing? Believe it or not, that was actually on the census. This was done for the US government for the census. And so you say yes or no. And if this is yes, it would click over one if you had indoor plumbing. Oh, I forgot, I told you that it was done for the census. The US Census completed in record time using Hollerith. Before this, the Constitution requires that a census be taken every 10 years. And before this, the census was, or the population was getting large enough that it was taking 10 years or more to tabulate the results from the census. I mean, you can get the results, but they're no good if you don't do anything with the data. And so this was remarkable. This little guy over here was used for sorting the punch cards based on different patterns that were punched into them. And in 1896, Hollerith formed the Tabulating Machine Company. That's TMC, and this is their headquarters building. And then TMC and two other companies merged to form the Computing, Tabulating, and Recording Company. Computing, Tabulating, and Recording Company. And they were selling these automated census or survey sorts of machines. Then in 1924, they changed their name. You may have heard of them now, IBM. So everything that we've covered so far has been building up to IBM. They can trace their roots back to Hollerith's 1880 design of that census machine. Okay, this is 1938 now. Cambridge University built a differential analyzer to mechanically solve differential equations. It was used to calculate artillery firing tables. That is, every time a new artillery piece is designed and produced, they go out and they shoot it at lots of different elevations and with lots of different kinds of shells and powder loads and all that kind of stuff, and wind. And then they develop these tables that go along with the artillery piece, saying if you want to throw if you're going to use this kind of shell and this much powder, and you want to throw it 250 yards, you have to elevate it so much. Those are very mathematically intense calculations. And these guys at Cambridge built this machine to do it. Now, interestingly enough, this is very, very similar to Babbage machine. One of the big differences is they used electric motors instead of a hand crank. So it was a lot faster. So that was 1938. In that same year, 1938, the Germans developed what they called the Enigma machine. Well, let me back up. They didn't really develop it. A Swiss company developed this, or a version of it. And their idea was they were trying to market it to international business companies that might want to send telegrams and stuff back and forth between their offices securely. And they also tried to sell it to governments and militaries for the same purpose, and they didn't really have a lot of success. The German State Department bought a couple of them and never really did much with them. Now, this happens to be something that students find rather interesting. And so I have done some work on I've done some research on how the Enigma works. So if I can find the right camera here. There we go. All right, so the Enigma, here I am, my lousy drawing again. Are you seeing the pad?
Yeah.
Okay, so the Enigma's got all these keys on here, and when you push a key, that creates an electrical signal, and that electrical signal went up, and boy, this is going to be clumsy if I have to keep switching back and forth, but oh, what the heck am I doing here? Okay, so you push one of these keys that generates an electric signal. That electric signal goes up and it goes through these rotors and it comes back and it lights up one of these bulbs. Now, when you close the door up here, these bulbs are labeled A, B, C, D, I think. I don't know what order. They might be in QWERTY order, the same order as the keys. But these rotors up here guarantee that when you push a button, you're going to get a light that comes on that's not the same letter as what you pushed. It is semi-random. So you push an X, maybe T lights up. And so what happens is the commander or whoever's sending the message dictates it in German to a secretary. The secretary gives it to the people operating this machine. One of them sits down and types that message in one letter at a time, and another person sitting right next to him over here writes down which letters light up. Spaces, you'll notice, were not encoded. So that means that when there was a space in the plain text, there was a space in the enciphered text, which actually turns out to be a problem. But the key to this are these rotors right here. Now, this one's got 3 rotors. You can see these, the big sawtooth on them. Those sawtooths stick up through these slots in the cover. And so we've got 1, 2, 3 rotors. There's actually a 4th one over here, but it's different. And I'll tell you how it's different in a minute. So let's go back to the white, or the pad here. And come on. Nope. Sync up. There you go. Okay, so we go through a rotor. Now, the rotors, I'm going to blow it up here. This is a rotor. On this side, around the circumference of the rotor, there were 26 contacts. Like that. 1 contact for each letter of the alphabet. On this side of the rotor, there were 26 contacts, 1 for each letter of the alphabet. And they go around the periphery, the circumference of the rotor. Now, the trick is that the 26 letters over here were tied to the 26 letters over here in a random fashion. Just randomly. Well, I wouldn't say randomly. It seems random. There's no obvious reason why this was connected to there. Okay, there's just no reason. This was a rotor. So when the power goes in, let's say this is A, and you type Z, Z comes up here and is hooked to A. Now, it's going to come out here, and maybe this is Q. Okay? And then next to it is another rotor. And these things, this set of contacts, and then the rotor right next to it has a set of contacts. These things were bridged. So Q became Q over here. And this rotor moved it to some other letter, which went over to the 3rd rotor, which moved it to some other letter. Then it went to that 4th rotor that I said was special. And the 4th rotor is special because it's called a reflecting rotor. The signal goes in, it's scrambled, but instead of moving on to another rotor, it sends it back to the 3rd rotor. And the 3rd rotor moves it to a different letter. It goes back to the 2nd letter, moves it to a different letter, goes into the 1st one, comes out, and then it goes to a bulb. So this thing has been scrambled about 7 times before the light bulb comes on. Okay, that seems pretty thorough, but it's not. It's just a text substitution is all it is. And somebody could figure that out in 20 minutes probably. So in order to make this even more exciting, every time you push a key, there is a mechanical mechanism that causes this first rotor to click 1/26th of a rotation in, well, if you're looking at it from that direction, it goes in a clockwise direction. So this guy clicks over one. Now that means that if you press two Z's in a row, you're going to get two different results because the second Z is going through a different rotor setting. And after this first rotor has clicked over 26 times, it causes the second rotor to click over once. And when the second rotor has clicked over 26 times, it causes the third rotor to click. And when it's clicked over 26 times, it causes the reflecting rotor to move. And so you get a huge number of possibilities in how this is scrambled. And the Germans, in their infinite wisdom, believed that this was secure. They bought this. Why do I not see anything here? What's going? There it is. Okay, so the Germans in the mid-30s, they knew they were going to go to war. They were looking for new security. They bought some of these and they played with them a little bit. And they said, yeah, these will probably work for us, but we want one thing added to them. And that is, let's see now, what am I doing here? What they added to it was a plug board on the front of the machine. And the plug board, there we go. Okay, so they made the front of the machine here hinged. So this front piece of wood would hinge down, and what you would see behind it are 26 plugs or jacks, 26 jacks labeled A through Z. And those jacks represented the final output of this rotor. So the signal comes in, gets all mixed up, reflects, goes back through, gets all mixed up, and instead of going to a light, it now went down here to the appropriate plug. So if it went in as a Z and it came out as a T, then it went over here to the jack labeled T. And the operator, before doing this, would put some plug, well, let me just first say, if the operator did nothing, then every one of the signals would remain the same. In other words, if it came out of here as an A, the light bulb for A would light up. If it came out as a Q, the light bulb for Q would light up. But if you plugged in a wire, that disconnected the automatic forwarding of the signal, and the signal was now going through your wire instead of to a light bulb. And so you go over here and you plug it in to another circuit. Let's say you went from T to F. Well, now the F light bulb would come on. So if it comes out of here as a T and you've got it bridged from T to F, the F light bulb comes on. So this is, for all intent and purposes, another rotor, but it's under the control of an individual. So the Germans requested that this plug board be put in for greater security, and they requested that there be, well, initially there were 5 different rotors labeled 1 through 5, and 3 of those 5 were placed in the machine at any given moment. So the way this worked is, originally they changed the code like once every 2 or 3 months, and then as war got closer, they started changing it more often. And it finally got to the point where they changed the settings every day. Yeah, I think at midnight is when they changed them. So the person, after the message got encoded, it was transmitted over a radio link using Morse code. It's just text. And at the other end, it was decoded by an identical machine, which had identical settings. Now that's important. You can't decode it unless you know the settings. So the settings are which rotors are placed in the machine. What order are they in? Is this rotor 1, rotor 7, or well, originally rotor 5? Ultimately, they had 8 rotors. As time went on, they added more rotors to make things even more complicated. So you have to know which rotors are in which position, and then you specify a beginning point using these letters. There's a window up here that you can look through and see what letter it's set on. So at midnight, this is set at, it's supposed to be random, but they found that the operators weren't very good at coming up with random 3-character or 4-character sequences. They'd use their initials or the initials of the month, or, you know, they just weren't good at random. But anyway, they were told where to set these. That was part of the setting, is this, you know, you have to know which rotors, what the original setting was for the beginning, and you have to know what the plug pattern was. So if you knew all of that stuff, then you could send a message. Well, after a little while, they made it even more complicated. They added a ring onto each one of these rotors, and that ring determined when the next rotor clicked over. So I told you when this one went 26 times, this guy clicked once. But that ring allowed you to define what position on this rotor caused that to happen. So now we've got these ring settings, we've got rotor settings, we've got rotor positions, we've got plug settings. All of that stuff has to be known by the sender and the receiver in order for this to work. It's pretty complicated. Okay, why are we not going anywhere? What just happened?
That hasn't changed much in modern times.
What hasn't?
The way they do radios in the military is they load it with the SKL, which is a little computer, plug it into the radio to ciphertext frequency hop, and if the time isn't exactly the same on all of the radios, it doesn't work.
Yeah, well, it's all done digitally today, and yes, you can channel hop now, which of course they didn't do, and you squirt it out as fast as you can, so there's less chance that somebody will pick it up, and there's all kinds of things that they do.
You'd be surprised how big of a pain in the butt it is to make sure all of the radios have the exact same time down to the second on every single vehicle.
No, actually, I wouldn't be surprised at it. This was very cumbersome, and it worked pretty well, but it sure took a long time. It sometimes was hours between the time that something was dictated and the time that the receiver got the clear text. It certainly was not in real time. Okay. So moving on now, the British, y'all probably know this story. The Polish people, the Poles had the best code cracking people in the world just before World War II. And they knew that this was going on and they were working on it. They actually got their hands on an Enigma. There was one being transported by train, and it was left in the train station overnight. It was locked up, but it wasn't guarded. The Germans were not too worried about losing one of these because they believed that even if the enemy had one, they still wouldn't be able to decipher the code. The Poles, however, did not have the resources necessary to build a machine that could decipher it. They figured out how to build the machine, but they just couldn't do it on their own enough. They deciphered some German text, but not much. So they brought the French and the British in, and the British started building this thing, which they called this is Colossus, is what they called it. And it was for decoding Enigma traffic. And by the time the war was over, the British were decoding Enigma traffic, sometimes faster than the Germans were. So they knew what was being told, what was being said faster than the Germans did. Now that's after they had the settings. Sometimes it took them several hours to figure out what the settings were for the day. Sometimes they never figured it out. Sometimes they figured it out 4 days later, and then they'd have to go back and decipher the traffic that they had recorded in that day. And maybe the information that came out of that decoded traffic was still useful, even though it was 4 days old. In 1938, the University of Pennsylvania built the ENIAC. That stands for Electronic Numerical Integrator and Computer. It was the first fully programmable general purpose electronic computer. These patch panels that you see here, thousands and thousands of patch panels, that's how you programmed the machine. You basically were wiring up the individual components. So this is the input to the ALU, and here's the input to the register file, and you had to put these patch cords in order to make it work. The patch cords represent the decode logic of the machine. Changing from one program to another could take several days because you had to repatch it, and then you had to test it to make sure that you did it right. This thing was also built for solving artillery programs, for artillery firing solutions. Well, I wouldn't say unfortunately. World War II ended before this could be used. I guess that's not unfortunate that the war ended, but it was never used for its intended purpose. However, the people that were involved in building this started a company called Remington Rand, and they sold a commercialized version of that called the UNIVAC. UNIVAC stood for Universal Automatic Computer, and it was the first successful commercial computer. They sold 46 of them. That was their definition of success. These things were so expensive that only governments and huge research labs, maybe corporations and universities, but they were very, very expensive. In in 1952, the UNIVAC was used by CBS television to predict that Eisenhower had won the presidential election, and they made that prediction with only 1% of the votes counted. But they were running statistical analysis on that computer, and they announced it early, and they were right. Now, in the 1950s, we had numerous computer companies, including Sperry Rand, IBM, General Electric, Digital Equipment, Computer Data, RCA, National Cash Register, Burroughs, Honeywell. They were all selling these mainframe computers that took up an entire room. Now, these computers were built using vacuum tubes. Most of you have probably never worked with vacuum tubes. The vacuum tube is basically a voltage amplifier. A transistor is a current amplifier. They both are amplifiers. And if you run them correctly, they can become digital switches. If you, let's take transistors, you all know something about transistors. If the input to a transistor is too high, you saturate the transistor. You force the output to its maximum level. If the input to the base on a transistor is too low, then the transistor is in cutoff and its output is as low as it'll ever get. When we're doing digital circuits, that's what we want to do. We want to drive the transistors into cutoff and saturation as quickly as possible. Well, vacuum tubes, sort of the same. Do the same, only instead of with current, we are doing it with vacuum tubes. Now, vacuum tubes are huge and they're slow, And they're very expensive, and mostly they're fragile. Very fragile. A lot of vacuum tubes have to be changed. Look at that. This is the ENIAC, 19,000 vacuum tubes. Now, at this time, vacuum tubes were basically hand blown. And so getting a new one was not just go down to the store and buy one. These things were burning out all of the time. There is a story that a moth got into the base of one of these vacuum tubes and was fried by the high voltage. That caused the computer to crash. Eventually, they found the problem. It turned out that it was not a one-shot deal, that insects, in particular moths, were getting in there a lot and causing problems. And so whenever the computer would crash, they'd say, it's another bug. And that's where the term bug came from, that we use when we're talking about computers. So these computers were only available to very large companies. However, eventually, the companies discovered that they could do all of their accounting and whatever else they needed the computer to do, but then the computer sat idle for long periods of time. And so what these people did is eventually they rented time on their big computer to smaller companies that couldn't afford their own computer, but they could afford to rent time on this one. So during the day, the computer owned by Shell Oil Company did work for Shell Oil Company, but at night it did work for, you know, Joe Blow's tailoring shop and maybe the little hardware store down on the counter's inventory and stuff like that. And so that helped pay for the computer, which meant that smaller companies could begin to afford them because now they didn't have to pay the entire price. They could rent part of it out and let somebody else pay for their time. And so that's sort of where we were in 1950. Now in 1951, this guy, whose name is Bill Shockley, William Shockley, and two other people, while working at Bell Labs, invented this thing they called the transistor. And that is a picture of the first transistor, which is about the size of a postage stamp. Now, because of bad feelings between Shockley and, well, Shockley basically took all the credit for inventing the transistor, and the two other people that he was working with were not happy about it. And so there were bad feelings. Shockley left and went to Caltech, where he continued his work on the transistor and eventually came up with something that you might recognize as a transistor. Could be mass produced and it could be sold to the public. So this is a discrete transistor here. In 1955, Shockley left Caltech and he formed a semiconductor lab at Beckham. He and 8 employees eventually left Beckham because Shockley was a tyrant. Nobody liked him. But he and these 8 people left to form their own company, and they were called the Traitorous 8. And among them were these two guys named Robert Noyce and Gordon Moore. With backing from Fairchild Instruments, they started the Fairchild Semiconductor Company. Now in 1958, a guy named Jack Kilby, who worked for Texas Instruments, developed an integrated circuit. That's a picture of the first integrated circuit. That's 2 AND gates right there. During the 1960s, computers switched from vacuum tubes to transistors and got much, much faster and much, much less expensive. Computing power that used to occupy an entire room could now fit beside a desk. That is a little computer in 1960. That's what we would call a mini computer today, but it's a lot smaller, it's a lot faster. It only takes one guy to operate it. Notice the guy's wearing white gloves though. We used to refer to the people that ran the mainframes as the priesthood. You were not allowed in this room because it was climate controlled. Only the priests were allowed in there, and they prayed to Father Syntax, and they got the thing working. But now you're getting down to the time where just one person can operate it. They do need to be specially trained, but they can. Notice what's back there. That's an oscilloscope. Oscilloscopes were used in finding problems. These things up here are paper tapes. They kind of work on the same principle as a punch card, except they are infinitely long, if you want them to be. And you take this, this is one paper tape that's just folded back and forth and stuck in this holder. I have one of these holders out in the garage that I use to hold little pieces of dowel. That's how old this stuff is in my garage. But if you take one of these packages and you put it right in here, you feed it through this guy, it reads the paper tape, folds it back up over here so you can store it. And now we're talking about being able to change programs pretty darn quickly. Okay, so these two guys started a little company which they called Intel. So they left Fairchild and they started Intel in 1968. In 1971, they produced the 4004. Now this is in 1971. In 1971, I was a sophomore, I guess, in college. And we were still using slide rules. Now the university did have a computer, but it was a mainframe computer. And you certainly couldn't use it while you were taking a test or anything. We had to use slide rules. This thing is a complete computer, no memory, but it's certainly a complete CPU. It's a 4-bit CPU, but it is complete. And it was enough to power a desktop calculator. It was actually a bit, it's called a bit slice machine. It did 4 bits, but it could be hooked to another 4004 and you'd have an 8-bit computer. And you hook another one in, you'd have a 12-bit computer, et cetera, et cetera, et cetera. So that was enough to run a calculator. In 1972, they produced the 8008, which was an 8-bit machine. And it was used in dedicated applications like vending machines, terminals, and calculators. This is how we used to talk to the mainframe at the university. You could type stuff in and get your answer back there. In 1974, they produced the 8080. This was an 8-bit machine too, but it was powerful enough to make a microcomputer feasible. Intel wasn't alone though. Intel had competition. Motorola had produced the 6800. National Semiconductor had produced the 3216. They were both competing with Intel. In 1974, there was a little company named Micro Instrumentation and Telemetry Systems, and they used that Intel 8080 to produce their Altair 8800. This was the first microcomputer. It was a kit. You had to put it together yourself. Or for $100, you could have them do it for you. Look at the address. The first microcomputer was designed and built in Albuquerque in it was produced to the public in 1974, but it took them 5 years to develop this thing. And I happened to live in Albuquerque at the time, and I was part of a computer group, and the guy that ran microinstrumentation and telemetry systems was also part of the computer group. So I got one of these in kit form, of course, and put it together myself. I was very familiar with this guy. So this is what their system looked like. The 8080. It was a 16-bit machine, 16-bit addresses, only 8 bits of data. These 8 lights right here represented the value, the data that was stored in the address, represented by these 16 lights. Notice how the lights are grouped into 3s. That's because at this time, octal, base 8, was the most popular way to talk about values. And so in base 8, you have 3 bits for each character in base 8. So this was a base 8 character, here's a base 8 character, and here's a base 8 character. And so you'd have, like 3, 4, 7. So 3, that would be both lights on. 4, this one on, these 2 off, and 7, all 3 of them would be on. And the same with the address. Now, what you would do when you first turn the power on is you put in an address of where your Bootstrap program is, and you hit a button, you hit a switch down here that says store that address in the register, in an address register. And then you could hit a switch that said begin executing at that address, and it would begin executing probably ROM, since you just turned the power on. And these lights would just go nuts as the address changed and the data changed, and here's like the flag register and stuff like that. This was extra. This is a floppy drive that you could put on there, and then you didn't have to put your programs in manually. You could do it on a floppy drive. And then they added the ability to use a monitor. This monitor connects over an RS-232 link, something similar to USB today. And this was all, of course, if you could afford it. During the 1970s, microprocessor brands proliferated. Each was different from the other. Heathkit was also a do-it-yourself company. Probably none of you remember, but Heathkit was a big company after the war. You could buy kits, put them together of electronic. I built many a Heathkit voltmeter, oscilloscope, television, stuff like that. These things came with every part you needed. The instructions for putting it together were practically a foot thick because they were so detailed. You couldn't screw it up if you followed the directions. So Heathkit got into the do-it-yourself computer market. Timex, a watchmaker, they also got in. This is a Sinclair 80. It's actually built with a Z80, which is another microprocessor, but these things also came in kit form. I built one of those. Here's a Sinclair, a little later model. Sinclair and Timex eventually merged, and it turned out anybody could do it. Apple's first model was wood. They built that in the garage, Steve Jobs' garage. Commodore designed one, but this was designed to play through your television set. Had really bad resolution on the screen, but you could hook it up to your TV. You could pick channel 3 or 4, and away you went. Zenith had one. Now this is pretty fancy. Look at this. It's got 2 floppy drives. Wow. Radio Shack. Radio Shack was actually the most successful microcomputer vendor for many years. This was a Radio Shack Model 1. The actual CPU was, I believe, in the keyboard unit. And this was an add-on. You hook it up right here. There's a ribbon cable between the keyboard unit and this add-on. The add-on allowed you more memory, printer port, serial port. It allowed you to hook a monitor. I think maybe you could hook the monitor directly into here, but if you plugged it into here, you could have more memory. So this could be a graphics screen instead of just text. And over here to the side, you could have 4 individually housed floppy drives. So it was quite a system. This is what I started with, and this is what most, in terms of not putting it together myself, this is what I started with. Canon. This one's got a little screen and 2 floppy drives, so this is all put together for you. Now that's probably only a 9-inch screen, hard to read, but it was there. Texas Instruments, they just keep looking slicker and slicker. K-Pro, 2 floppy drives, monitor, keyboard. However, the keyboard is hinged, and you lift it up, you can snap it on with these 2 guys right here. That covers all of this, and it looks like a suitcase. You can't see it, but over here on the side, there's a handle. This was called a transportable. You still had to plug it in, but it was easy to move because it was only 1 piece, as opposed to that Radio Shack machine, which if you moved it, you would have to move 1, 2, 3, at least 7 pieces, not counting a printer if you had one. Osborne, same deal. Little tiny screen, couple of floppy drives, but it folds up, latches in place. Compaq, same deal.